OpenShift networking might be one of the most misunderstood capabilities within OpenShift Platform. There's a lot to it. Pod network, service network, bridge networks, microsegmentation, fast data path, software-defined, load balancer, service mesh. You can breathe now. Okay, I won't be able to cover all of it in a single video, but my goal is to explain fundamentals of the OpenShift networking. So strap yourself in, because in the next few minutes, things will become way less complicated. Well, at least I hope so. Let's start with the basics. When you first install OpenShift, the configuration steps asks for 3 networks: cluster network, machine network, and service network. Each node will have at least one physical network connection or highly available bond if you're running production. There is an OVS bridge called BREX attached to this primary interface with the IP assigned from the machine network pool. By the way, this is the only external network that is required in OpenShift, and it's the one to make sure IP addresses are not overlapping with the rest of your infrastructure. The other 2 are not accessible by default from outside of your cluster. Now let's patch this network to another OVS bridge responsible for integration. This is how we get to the cluster network from the list. Please note that the prefix on my host is set up to /23, giving me about 500 available IPs. The supernet though is defined with /14, which gives me the ability to place every new host in its own layer 3 cluster network. The last on this short list is service network, which also runs as part of my OVN software-defined network. Service network provides internal load balancing and DNS capabilities within the cluster. Thanks to service networks, it is possible to keep a stable IP for pods or VMs, or to share one IP for multiple pods implementing the same service. How do these networks work with our workload? Let's deploy 2 pods. Each one by default gets the IP from the cluster network out of 500-ish IP pool we've mentioned earlier. We can now internally load balance or expose running application with the service network IP. Both TCP and UDP ports are supported. Let's add 2 virtual machines, and you can see they also get the pod cluster network IP. However, they get NAT treatment from the pod down to the VM itself. If you try to find out the IP address from within the operating system, you notice all of them come back with 10.0.2.2. You can still access other VMs with their pod IPs though. Let's add the second OCP node with its own physical interface. Add the BRX with our external machine network, patch integration bridge, then cluster and service network. Please note the cluster network IP is now in a different layer 3 network than the first node. Finally, let's deploy some pods and VMs and physically connect the OCP nodes with a switch. But wait, didn't I say the only external network is the machine network? How are these pods talking to each other if they are not connected via an external network? Well, it's because nodes are running tunnels between each other and encapsulating all the pod network traffic into Geneve tunnel-based overlay network. The easiest way for me to understand this is to imagine these are nested layers of abstracted networks. First, the underlay network, often based on VLANs, is nesting another overlay network like a VXLAN or Geneve. This helps with scalability and avoids the limits of traditional VLANs. That wasn't too bad, right? Before we jump into some practical examples, let me cover one more use case. Let's add another physical interface or aggregate. To fully take advantage of OVN software-defined networking, we're going to create another OVS bridge and call it BR data. The name is not really that important, but we want to ensure the attached interface is trunk port carrying all the VLANs that we want to pass to our pods, and more likely to a virtual machines. We define these VLANs with a network attachment definition, CRD, in this example VLAN 10 and VLAN 20. Now let's make our virtual machine accessible to the rest of our infrastructure via routable IP. In my case, 192.168.10.5 IP. Please note that unlike the pod network, we no longer need to NAT the VM. The virtual machine communicates over our dedicated data network, and because it runs through the OVN bridge, we can still apply security policies for microsegmentation. Let's add the equivalent on the second node, and now the picture is complete. But wait, there's more. For fastest performance, we could eliminate the bridge and assign the MAC VLANs, SROV VFs, and PFs, or even allocate the entire host device to our workloads. Too much? Let's leave these accelerated networks for another video. Please let me know down in the comments below if that's something you would like to see. Now we jump to the live system to explore what we've learned. The most basic configuration for our physical network can be defined with this example. We specify the nickname, its routable IP address, also known as a machine network, the DNS server or servers, and a default gateway. In production though, you will most likely aggregate the link, and here's an example from my system on how this would look like. This time, next to the IP address, we can specify multiple physical network interfaces and aggregate them together with active-active LACP bond for better resiliency and performance. DNS and routing stay the same as with the previous example. Okay, let's jump into one of the already deployed nodes and inspect the results. The BREX, as we talked about a bit earlier, gets assigned a machine network routable IP, and in this case also a virtual IP for API access. OVN K8S MP0 interface is allocated with the cluster network. Expanding our OVS configurations shows the BREX attached to the bond 0, which as we already know aggregates multiple NICs into active-active connection to the rest of my networking infrastructure. It is also patched up with the integration bridge that manages the OVN Geneve tunnels with all the other controllers and workers in my deployment. If we compare what we have seen with the second system in my deployment, BREX in this case runs in the same layer 2 network but has a next incremental IP. Please note that the cluster network allocated to OVN K8S MP0 interface runs in a different layer 2 network. Let's copy the IP and try to ping it from the first system. It is indeed pingable, and tracepath exposes what we have suspected to be the case earlier, the layer 3 connectivity with multiple hops. Finally, let's expose the routing for our connection to the other node, and indeed we see a gateway used to connect cluster networks. Even though the cluster network appears to be routable, please keep in mind that the scope of the routing is limited to our cluster only. You won't be able to ping these IPs from outside the cluster. With this knowledge of how the OpenShift native networking sausage is made, let's get into the OpenShift itself and deploy some workloads. I'm going to start with deploying two simple BusyBox containers running in a Kubernetes pods. Let's also ensure they land on a different physical hosts. Starting with the first BusyBox pod, you can see by default OpenShift assigns IP from cluster network, or as we also like to call it, a pod network. Nice. Let's save the IP and start the web server on the pod listening on port 8000. Then create a simple page displaying our IP. Now switching to the second BusyBox and inspecting its IP, show yet another pod network IP. Let's see if we can access the other pod's web server over this network. Success! Just like on the first pod, let's create a web server here with its own IP listed on the web page. Moving to OpenShift Network Services next. As we mentioned before, Service Network provides internal load balancing capabilities within the cluster. We need to specify the label for the pods that we are planning to select and the port to expose and load balance. The service assigns a new IP from the Service Network IP pool allocated during the installation. Please note that the service network is also only accessible within the cluster and not externally routable. Since we haven't tagged our pods yet, the service won't be able to select our web servers for load balancing. Let's do that now and have both of the BusyBox pods be tagged with the same label. Now, the service can finally select which pod to load balance. We can test it by jumping back on the BusyBox one and getting the web server. As you can see, the web page changes with few attempts. Even though the web server is already accessible to other workloads within my cluster, I can take a step further and expose it externally with the ingress controller. For that, I will create an OpenShift route and map it to our BusyBox service. With the routes, OpenShift generates a URL pointing to my load balanced web server. I can not only see it within the cluster, but outside as well. Trying to curl it multiple times from my laptop also shows the load balancing is working fine. Please note that the routes feature can only expose web services on either port 80 or 443. Other words, you won't be able to do the same for, let's say, your databases or RDP access. For those, you would need Metal LB. but we're already deep enough in this rabbit hole. We should keep the metal LB conversation for another video. Since our pods are all connected now, I should also show you how to secure them. For that, we need the network policy, which also takes advantage of the labels just like we saw with the services. Even though I can be super granular with the permissions, in this example, I'm just going to block all the traffic. And now to validate it is effective, I try getting to the web page and it's just no longer accessible on the pod network. We talked about the pods and containers, but how does the networking look like for OpenShift virtualization? We're going to deploy two simple VMs with all the defaults. Each VM just gets a pod network IP. However, unlike the pods, if I terminal in and try to expose its IP, instead of my pod IP, I see 10.0.2.2. Please note the same happens on the other VM. As a matter of fact, each VM by default will think they run on 10.0.2.2. Don't fret, we don't have any duplicate IPs. Instead, OpenShift is natting the access to the VMs. But we can still use their pod IP to ping them, and just like we've seen before, this is a layer 3 network with some hops between VMs. The other capabilities like services and routes work the same way as we have seen with the BusyBox pod. I know what some of you are thinking. Why go through all that trouble, especially for virtual machines? With VMware DV Switch, you don't need to be bothered with overlay networks, services, routes, etc. You can just hook up straight up VLANs to your VMs and be on your merry way. I have good news. You don't need to use pod networks with VMs. You can just hook up your VLAN straight up to the same way you do with the VMware DV Switch. It's a two-step process. Step 1. Map a new local net name with your bridge, either BREX or any other custom bridge you might have created. Use a default namespace if you want all your tenants to have access to it, or your own namespace for isolating it to yourself. Step 2. Create network attachment definition, matching the previously created bridge mapping and the namespace, and tag it with the right VLAN. That's it. You can now deploy VMs with, in my case, VLAN 1105, and this is how it works. When you deploy a VM, simply customize Network Interface tab, edit the interface, and replace pod networking with newly created VLAN. There's a way to have an internal IPAM hand over the IP, but in my case, I want to allocate IP myself. So in scripts, edit the cloud init section, check the add network data, and finally enter the networking details. The VM comes up with a specified IP address, and if your VLAN is routable like the one in my example, you can just have direct access as with more traditional virtualization platforms. Also, please note there's no NAT in between, so when accessing VM directly, you can see the IP in your IPA output. What we just created is called a secondary network, or as some folks call it, a local net. And there's one more type of local net that I want to show you before we wrap this up. If you ever use an OpenStack, you might be familiar with a non-routable tenant networks. The use case is for multiple teams or projects to share the same environment and to give them the ability to create their own internal and isolated networks. Multiple teams might want to choose to have overlapping IPs, and we need to accommodate this as well. Introducing Layer 2 secondary networks. There's no need to create bridge mappings for layer 2 networks. This is an overlay network. All you need to specify is the network name and the project or namespace. Attaching layer 2 networks works similar to what we've seen with VLAN networks. Simply customize your VM and replace the existing pod network or add the new layer 2 private network to your VM. To draw a full circle and get to the finish line, let's just discuss microsegmentation. I already showed you the network policies for the pod networking. Securing the secondary networks works very similarly. However, instead of network policies, we use the multi-network policies. We specify name and select the private network that we want to secure, then specify ingress and egress rules. Okay, I know it's quite a lot, but if you master these fundamentals, the rest of the platform should be smooth sailing for you. Also, I have 3 good news for you. 1. If you missed something or certain concept was not clear, you can always go back and rewatch it. I have put the chapters in this video for your convenience. 2. I'm including all my YAML files in the video description for your reference. 3. If you have questions or concerns, let me know in the comments down below and I'll do my best to respond. In any case, I hope this video has been helpful and thanks for watching.